Well, I would like to thank Prof. Talvitie for coming and giving this guest lecture today. Her research area is model-based reinforcement learning. And let me just turn it over to you.
Great. Hi, folks. So I was trying to figure out what to talk about today, and I know you've already. So the main thing I want to talk about is the thing that I'm almost always excited to talk about, which is model-based reinforcement learning. And I know that you've studied a couple of core ideas there, like DynaQ and Monte Carlo tree search and stuff. So I don't know. I guess I ended up doing this kind of stream of consciousness thing that, I'll tell you a little bit about some things that I've been working on lately and will be working on soon. Some kind of, I don't know, I think pretty open problems in model-based reinforcement learning. And that will also kind of lead us to just briefly touch on some existing important ideas in model-based reinforcement learning. It's going to be light and breezy. I probably prepared too many slides. So, we'll just take it as it goes. I've got the participants window open. If you ever want to flag me down and ask me a question, you can just throw up your hand and I'll pause and we can chat. Okay. So let's go. So I titled this talk "A Model-Based Reinforcement Learning Wish List," and you'll see why that is eventually. So the main thing I want to talk about. Oh, I'm in the wrong thing. Hold on. There we go. So if you imagine playing a video game for the first time, right? It's like a new video game to you. What do you imagine doing? You kind of fiddle with the controls. You see what happens on the screen. Eventually you start to get a sense of like, oh, when this happens, then this is going to happen next. Or when I do this, then this is going to happen. And then eventually you start to be able to use those predictions to make good decisions. You start to be able to say things like, oh, well, I want this to happen, so I should do this and then this and then this. Or I don't want that to happen, so I'm going to do this to prevent it, or that kind of thing. So I think that hopefully feels very intuitive to you. To me, it certainly feels like how I navigate a lot of the world. And I would characterize that as pretty clearly model-based reasoning. We're kind of learning to make predictions about the world. We're sort of creating a small version of the world in our imagination, and then we're interacting with it in addition to interacting with the world in order to learn and make good decisions. So one of the things that's interesting, I think, about reinforcement learning at the moment in these times is that even though that is a pretty sensible idea, and I think it's probably what most people think of when you say like, oh, I have a program that's learning to play a video game. They probably think it's doing something like that. That's not what you've been learning about this semester for the most part. So things like Q-learning and SARSA, those are model-free approaches. They make no attempt to make predictions about what's going to happen next in the world. They only try to predict whether this action or that action is going to work out better or worse for me, right? So, I think there's an interesting gap there where in human conscious experience, at least, we seem to feel like we do this model-based thing, but then computationally, it's way more common and way more successful to do this model-free thing. And so maybe by the end of today, I will make it a little more clear why that is and sort of what needs to happen to close that gap. So just to get us all on the same page, when I talk about model-based reinforcement learning, I'm talking about this kind of abstract picture. We have some environment, and that's the real environment, and there's some agent that's interacting with the environment. It's interacting with the environment via some actuators. It could be like the joystick in the Atari 2600 to play Space Invaders or whatever. So as the agent interacts with the environment, it receives observations. And what does it do with those observations? Well, in model-based reinforcement learning, we are imagining that it's at least partly using those observations via some process, and we don't need to talk about the details here, but some process called model learning. It produces a model, and the model is a lot like the environment, except it's in the agent's imagination, and it's smaller, it's simpler, and it's orange for some reason, okay? So That's the idea there. And then in some other part of this loop, the agent via some process, we don't need to know the details, but we'll call the process planning, then makes decisions about what to do. And so it sort of turns its predictions into decisions, and then it can take actions in the environment. Okay, so just like roughly speaking, when I talk about model-based reinforcement learning, this is what I'm talking about. The distinction to model-free reinforcement learning is this orange box, right? The model, we're explicitly learning to make predictions about the dynamics of the world, and that's the distinguisher. It seems like it should only be a plus. You'll see very quickly that it's not. So why should we even pursue this? Why am I about to devote an entire, however long, talking about model-based reinforcement learning? If Q-learning works, why should we look elsewhere? So one reason is that model-based approaches, at least intuitively, it seems like they are a pretty good use of data. So here's another Atari game. This one's called Montezuma's Revenge. And so this is an interesting game because so the player plays this like explorer person, and they have to first jump over this gap, climb down the ladder, walk against the conveyor belt that's this dashed lines, and then jump over to the next platform, climb down, then move over, and then jump and get a key. And that is you can imagine that this poses a big challenge if you're just using Q-learning, and you'll like jiggle around for a long time, and eventually you'll randomly accidentally get the key, right? And so what does the agent learn if you're doing Q-learning? Well, it learns that it's good to be next to the key, right? And that's very little to learn for all of the time that it took to jiggle your way over to the key. Now you could do something like eligibility traces, which I think you might have covered by now. And so if you you'll really roundabout route. So whereas in contrast, if you're learning a model, then all of that time that you're spending not getting the key is not wasted. You're still using that time to learn about the world, right? And then after you've figured out, oh, I can get reward this way, then you can probably use what you know about how the world works to just reinforce that, to plan to do it again, maybe almost immediately, right? So it's a good use of data. Another reason is to think about problems that take a minute to learn, but a lifetime to master. And of course, that is the classic slogan for the board game Othello, sometimes called Reversi. But it's not just a trite marketing message, it's a real thing. So sometimes there are problems where it really genuinely is easier to learn the rules than it is to learn what to do with the rules, right? So it's very quick to figure out what you can do and what will happen when you do it. But maybe the value function is very complicated, right? And so it would take a long time to learn a good value function. So this is another good reason to want model-based methods, is that there are problems where a model is probably going to be better at generalizing and be more sample efficient to learn, and then you could take advantage of that in learning a more complicated value function. Of course, there are problems the other way, right? So there are problems where the model is really hard to learn, but you can still learn a good value function. So one of the things I think about is like kicking a soccer ball. I don't think any of us actually has a good model of what happens when you kick a soccer ball. It's actually a very complicated system, right? There's all these like squishy physics going on, and deformations and elasticity and spin, and it's like a very complicated system. But you can still, if you practice enough, you can still learn to kick a soccer ball pretty accurately to wherever you want it to go. So that's an example that might be the reverse, where you might spend a whole life not get it, but you can spend um, a few hundred hours and be an expert at kicking a soccer ball. And also another good reason is that animals seem to do it, and that includes humans, right? So this is pretty well understood. Lots of behavioral studies have been done that seem to indicate that animals like rats and humans and dogs and monkeys and stuff do both of these things, have both model-free or habitual behaviors, and then also model-based or goal-directed behaviors. So one example from rat behavior literature is, they make a rat maze, and they habituate the rat to the maze, and it learns a good route to the food, and then they block off the route. And so the interesting thing is that the rats can very, very, very quickly start using an alternative route. They don't have to kind of undo their learning and then redo their learning to find a new route, which is what, for instance, Q learning would have to, because it would have to learn a whole new value function. It's not able to just reason, oh, like I could just do this other thing, right? So the core thread, like the big question that's driving me these days, or that underlies a lot of the questions that I've been asking is this one: how should we use models? Like, say we are going to do model-based reinforcement learning. Okay, that means we're going to learn a model, right? So how should we use it to get the most out of it? And the most common thing to do, the most reasonable way to think about this is just to use it to get more data, right? So like you can live in the world and get as much data as you can, but maybe it's expensive to live in the world. Maybe you have spare compute time. Maybe it's hard to get enough samples. Maybe it's dangerous to act in the world. You could break something or damage something. And so maybe you learn a model and then use it to get more data. So that you don't need as much data from the world. So what is more data good for? Well, one thing it's good for is to refine your policy parameters or your value function parameters. So you've had this experience probably by now if you've implemented typical like Q learning or SARSA. Like you have to run this thing a bunch of times, right? It has to collect a whole bunch of data. It's not necessarily learning much new every time. It just kind of has to settle all of its parameters, right? It has to do lots of iterations just to kind of move its way through the optimization and find that good policy. And another good reason is to propagate value information. So like if you have encountered, like you're in a grid world and you find a happy square, then you need more data in order to propagate that all the way back to, say, the start location, where that information can finally affect how you make your first decision. So if you want to use a model to get more data to do this, right, to just like get more iterations, propagate things back, I'm going to argue that pretty much all you need in order to make that happen is to just replay experience that you've already had. So this brings up the first of several kind of key model-based ideas that I wanted to bring up. So this is called experience replay. This is a classic approach. I'm sorry, I was trying to put citations in this and I guess I forgot to put it in here, but it's from like 1990 something. So it's not limited to reinforcement learning. It's used in supervised learning as well. It's a really simple idea. It's just like, oh, well, I wish I had more data than I have. So in every step, I will take my current experience and I will save it to a buffer where I'm remembering past experiences. And then I will train my value function on the current experience, just like usual. But then I'll use some extra compute time to also load K more experiences from my buffer of past experiences, and then train my Q learning on those as well. So the result is it's as if I'm getting more data, right? So if I do K of these, then it's like I'm getting 100 more data points than I would get if I were just using the ones from the real world, right? It's just a very simple idea. It's called experience replay. So I said this is a model-based idea, and then some people sometimes question that, right? Like, is that actually model-based? Like, did we ever really learn a model? And I think that's a fair question, and this, I think it illustrates the fuzzy barrier between model-based approaches and model-free approaches. Because on the one hand, we're not actually learning a model, right? We're not doing another learning process. We're not optimizing some other function. But we are doing extra work to kind of plan, right? We are taking this buffer and using it to augment our data to get more data. You know, and on the other hand, we're just memorizing stuff. We're not actually learning how the world works. We're not generalizing to new states. We're not, you know, all we're doing is remembering what has happened. But on the other hand, isn't that a kind of model? Like, it's the kind of stupid model. It doesn't tell us about things that haven't happened, but as a model, so I don't know, it's not ridiculous, I think, to call that a model. And some people would call experience replay the simplest possible model-based approach. Excuse me. So I'm going to show you some experiments from a recent paper that are all in some Atari 2600 games. And I'll use it to kind of give some experimental, I don't know about answers, but experimental kind of illustrations of the things that I wanted to talk to you about. So I'll show you results from 6 games from the Atari 2600. It doesn't much matter what they are. You might recognize some of them. The main thing that I want to point out from these images is just that they're all very different from each other. So like in Asterix, you're moving up and down and left and right. In Sequest, you're still moving up and down and left and right, but you're also shooting things. In Beam Rider, it's more like a first-person view almost, or a third-person over-the-shoulder view, where like the scenery is coming toward you. In Space Invaders, you can only move left or right, and you're shooting things, and things are being shot at you. In Qbert, you're moving diagonally along all of these squares. And Ms. Pac-Man, of course, is this navigation game. You have to move through this maze and avoid the ghosts. Like, they're all fairly qualitatively different. They're not just the same as each other. And so I'm about to show you some plots. And in these plots, I'm using a DQN agent. I don't know if you've studied DQN yet, but either way, it's okay. So DQN, it stands for Deep Q Networks. Really all it is basically Q learning, except it's using a convolutional neural net as a value function. And of course, there's more details, right? So like DQN, they have to do all kinds of weird training tricks in order to make this actually work. You know, neural nets are kind of finicky and you have to kind of coddle them in certain ways. So you know, it's DQN is more than that, but at its heart, it's just the Q learning update, and it's using a big giant convolutional neural net as its value function representation. So here are some results. So here are here's what DQN can do with 100,000 experiences in each of those games. So it interacts with those games for 100,000 frames. And then we trained it that long, and then we evaluated the policy that it had learned, and this is how good each of those policies was in each of the games on average across all of the trials. So, you know, I mean, it's hard for you to see like whether this is good or bad, but it's like learning something, right? That's fine. Here's what happens if you do the same thing, but you add experience replay. So I know this is a little weird. If you know something about DQN, you know it already is doing experience replay in a way. So what I mean by that is I'm taking DQN and I'm just doing more updates on past experience. So for every update that GQN was gonna do, I'm doing 100 more updates that are just using experiences that are drawn from the past. So that's like experience replay. We're just doing a whole bunch of extra updates on past experiences. And here's what happens. So it's better. Pretty much in every game, it helps, right? Like that's exciting. You know, there is still an open question. Like we're spending 100 times more updates to get this improvement, and is that actually worth it? I'll show you in a minute. Okay, so that's one thing we can do. We can replay experience, and that allows us to more quickly kind of reach the point where the value function was going to get to more quickly propagate information that we've learned, all of that stuff. But I don't think that's enough, right? Like I don't think that's everything that you get from collecting data in the world. For instance, there's one issue with experience replay, which is that if you're remembering things from the past, and maybe you've had this experience where it's like something particularly good happened to you or something particularly bad happened to you, and it just keeps running through your mind, right? You just keep replaying it. So that's one thing. But also, maybe since then, you've learned some stuff, right? Like maybe what you did back then is not what you would do knowing now what you know. And so that information is all off policy. Ooh, I have a flashing something, chat. Were those scores after a set number of real life experience steps or after the value function converged? It was after a set number. So let me go back to that. So those were after 100,000 real life steps. So right, that's all stuff that from the old policy, and now you're doing a wholly different policy. And I kind of do that thing where we're like obsessing over a past event. I think a lot of what we do is not just like, here's what happened, I'd better learn from it, but also, I should have done this, and this is what would have happened if I had, right? So another thing, if you had a model there was a little more capacity than just past experience recorded, then you might be able to do something like get more on policy experience, like get more data that is like what you would do now, which is more informative for your value function, right? So in order to do that, you need a model that's capable not only of showing you what has happened in the past, but is also capable of imagining a different action, like taking a different action in those past situations and then imagining what would happen next, right? So that brings us to DynaQ, which I know you studied. I'm not going to belabor it, but just to summarize it in the framework that I'm trying to set up, right? In DynaQ, in each step, you have experienced something, you save that to your buffer, and you know, typically you would train Q on that current experience. You don't want to lose track of the most recent stuff is the juiciest stuff, right? That's all super on policy. It's what you want. But then also you train your model. So now we're not just storing some buffer, we're storing a model, a parameterized probably model of the world. And then we'll load K states from the buffer, and then we'll choose an action to take in each one of those states, probably using our current policy, but you know, or randomly or whatever. And then use the model that we've learned to predict what the next state would be. And then we update our Q function based on those imagined experiences, right? So now it's not something that really happened. It's like I was in that state, but this now I would, in that state, I would do this, and what would happen then, and now I'm learning from that, right? So I'm relying a whole lot more on this learned model at this point to get things right. And of course, DynaQ raises a whole bunch of interesting questions that I'm not going to spend a whole lot of time thinking about. Things like, well, okay, we have to pick some initial states. Which ones should we pick, right? I don't know. You know, some interesting work tries to pick states that are likely to cause big updates, which, you know, makes sense. You don't want to pick states that you already know everything about. You want to pick states where you're learning something. And then also, once you have an initial state, how should you choose the action, right? So I think an on-policy action choice makes sense, but there might be smarter ways to maybe, again, you should pick an action that would be informative rather than what you would really do right now. I don't know. So the analog, we sort of took that and we did the analog of DynaQ, but with DQN. And so in these plots, it's all with a perfect model. So there's no question about the model's accuracy here. It's all just like, say we managed to live our greatest life and we learned a perfect model, then what would we even do with it, right? And so the question now is, well, all right, so if I do DynaQ, do I do better than with experience replay? And so here comes DynaQ in blue. And, when we did these experiments, we were pretty surprised, actually, because it's not much better. Honestly, it's maybe only better in a couple of games and only by a little bit. And so that was pretty surprising to us because it takes a lot of effort to learn a model. Especially if you're in a big complicated world like Atari and you need to do a big convolutional neural net or something to represent this thing. It's a lot of effort to train this thing. It's a lot of effort to represent it. It's a lot of effort to use it even. Like, it's not nearly as easy as just sampling from a buffer. And it barely gave us any benefit at all, right? The conclusion here was basically, well, why bother, right? Just do experience replay. And especially that's true if you compare to what would have happened if instead of getting those extra 100 steps from the model for every step, we just ran DQN for 100 times more. So if we do this, if we get 100 times more data just from the real world, we are now running a million frames. That's so much better. Getting experience from the real world is so much more valuable than either of these things, than data from either of these approaches, right? And remember, this is a perfect model. This is not like, oh, the model's got error or something. We're literally getting the planning experience from the real world. The only difference here is how that experience is distributed, right? Like which experiences are we training on? That's the only difference. And so we were shocked, quite honestly. We had no idea what to do with this until we had a realization. We were trying to figure out, like, what is it that's missing? What's more valuable about the real world experience than about the model experience? And it turns, the thing we thought of was that what's missing is exploration. I have a question. Hang on. Is there a reason why DynaDQN improved on some games but not on others? I don't know. The truth is that Atari is just weird. It's kind of hard to draw too many conclusions from like individual results because games just have all kinds of funky things about them. So I don't know. I would suspect that in some games it turns out that learned model, or sorry, that the on policy experience is more important, that like imagining a new thing to do rather than what you did do turns out to be more consequential than in some games than in others, but I'm not sure. So what's missing is exploration, right? In experience replay and even in DynaQ, like, we never actually travel very far from where we've been. We never, we basically only ever see things that we've done or things that are very close to what we've done. And so, whereas when you're interacting with the real world, you're often encountering new states, right? That you've never seen before, and maybe those are important. So if we want our model data to be as valuable as world data, then we need it to replace some of the exploration we would have done in the world. which means that we need to be able to imagine reaching new states that we've never seen before, right? And just to illustrate why, like really hammer home that this is a good idea, we did this experiment again with perfect models. So this is not about model error. This is just perfect model. The only question is, how are we using it to get data? And so right now the plots are incomplete. I'm showing you the exact same information we looked at before, just in a different format. So the blue bar that goes up, that is the DynaDQN, right? So that's basically DynaQ. And then the lines, the benchmark lines here, the colors are off because I had to recolor things a little bit and it didn't go very well. But the sort of yellowish line on the bottom, that is just regular DQN trained for 100,000 steps. The greenish bar in the middle, that's experience replay. And then the orangish bar near the top, that is the DQN trained for 10 million steps, right? So that's where we want to be. Like, we would like ideally for 100 extra steps of planning to get us to be equivalent to 100 extra steps of real life experience. So what I'm showing you here is the normal DynaDQN stuff where it's like, oh, if I'm going to do 100 planning steps, I'm going to do 100 one-step updates. I'm going to grab 100 initial states and do one step away from them and then update those one-step rollouts. But you can imagine reshaping planning. It doesn't have to be 100 by 1. It could be 2 by 50. Right? It could be 20 by 5. Like, you can use those 100 model transitions however you want by generating longer rollouts, but fewer of them. And so now I'm going to show you what happens when you consider deeper but narrower planning shapes, again, with a perfect model. Here it goes. And like this plot bowled us over. This is so weird. Again, every single one of these is using the same perfect model, but we found that if we allowed the rollouts to go further, then we got significantly more value out of them. And from the last slide, the sort of speculation here is that it's because those longer rollouts are allowing us to replace some of the exploration that you would do in the real world. And so it makes those experiences more valuable than if you stick close to what you've already seen. Somebody's probably going to ask, like, why is it in Sequest that that sometimes the planning agent does better than the one that's trained from real world experience? I do not know. Sequest is weird. Sorry. What do I mean by longer rollouts? Oh, great. So, oh, wow, that's an important question. Thank you for asking it. So we'll take an initial state from the buffer, and then we'll predict the next state, right? That's the normal Dyna thing. And then we'll take that predicted state and we'll pick an action and we'll predict another state from that, and then another state and another state and another state. So if we're doing, say, length 3, like this 33 by 3, now we're doing 33 3-step rollouts where we predict the next state and then the next state and then the next state. That's 3 steps. And then we do backups for each one of those 3 steps. And we do that. We pick 33 initial states instead of 100 initial states. Did that make sense? Great. So you can imagine that because it's long, like we're allowing the model to generate longer trajectories, it can get farther away from what we've already seen, possibly generate interesting, useful, important things in the future. So this tells us a lot about what we need in order for our models to be valuable. And so it adds to what I'm calling my model-based reinforcement learning wish list. So I think one of the things this tells me is that in order to get the most out of the model, it really needs good, powerful generalization. It needs to be able to make predictions in unfamiliar states, and they need to be reasonable. So that means I need to be able to take local experience and turn it into global knowledge, right? Like somehow I need to draw big conclusions from limited experience. And the only way I know of about how to do that is that we need our models to now have a lot of built-in structure and bias, and possibly you might call it prior knowledge, but just like some, big generalization comes from big assumptions. And so, that has implications, for what we're doing. If we are trying to learn like super open, fully general, universal function classes, then we may not get the kind of generalization we need in order to see the effect that we just saw. Are discount factors used in the rollouts? If so, do we have a kind of vanishing reward effect for very long rollouts, and how would we combat that? No. So we're treating it as if this trajectory, like as if the agent just experienced this trajectory. So for each step along the trajectory, it just does a Q-learning update as if it was experiencing that rollout in real life. So we need powerful generalization, and we also need what I'm going to call temporal composition. So we need the ability to roll the model out to get these rollouts that we've been talking about. And we need that in order to do this thing where we can replace search or exploration in the real world, where we can explore without having to really explore. So those are some things we need. Now I want to tell you about a little piece of, I'll tell you about a piece of work that I did that addresses some of the barriers to having those things, because it turns out it's not so easy to have those things, particularly the temporal composition thing. So let me tell you why that's a problem. So here's a little simple video game. You can see there's like this little spaceship at the bottom and targets at the top. The spaceship can move left and right, and it can shoot bullets. And the bullets, eventually, if it hits the target, you get points. There's also these white dots up there, and the white dots are moving back and forth. And if the bullet hits the target in the same column as the white dot, then you get bonus points, right? So it's very simple. Not a very interesting problem at all. Which is why it's so galling what I'm about to show you. So the typical way to learn a model would be to take this experience and then consider each one of those frames, each one of those experiences a state. And now, how are we going to learn a model? Well, we know a lot about supervised learning. It's it's just a very well understood set of tools, and this kind of feels like a supervised learning problem. If you imagine this as a training sample where it's like the input is, I was in this state and I took this action, and then the learning target or the output is, and then I ended up in this state. And so we have all kinds of things that we could throw at that problem. And so that's what we would do, right? We would just sort of make a whole bunch of training samples that look like this. I was in this state, I took this action, I ended up in this state. And what we're trying to do there is to minimize the one-step error of predicting the next world state from the current world state, right? So we imagine that we're in some state that we have observed, and then we want to predict the next thing that we're going to observe. So hopefully that seems reasonable. It's a mess. Let me show you why this fails. So I'm going to, for the purposes of this little side note, I want to talk about a different planning algorithm. That's a very simple one. And the reason I used it in this work was mainly because it was possible to do some math on it. So it's called one-ply Monte Carlo planning. It's a very, very simplified version of Monte Carlo tree search, as you'll see in a second. So just to make sure we're all on board, this is that you're in some state, S1, and now I want to know how good it is to take action A. So in my imagination, I will use my model to predict what would happen if I were to take action A. I would end up in this state. And so now I have to evaluate that decision. Is that good or bad, right? And so you are familiar now from Monte Carlo tree search with the idea of a rollout policy, right? So we'll take this state and we'll now behave in some particular way, usually just randomly, and just imagine a whole long sequence of decisions and states using the rollout policy. And then at the end, we'll get some report back about how good that was, right? But that's not enough. We have to do it a bunch of times. So, you know, this is where it differs from Monte Carlo tree search, because in Monte Carlo tree search, you would pull that back and you would build your tree out. But in one-ply Monte Carlo, we're not going to build the tree. We're just going to do rollouts from this one state. So we just keep taking action A and doing more rollouts. And then we get an average of how good that is. And then we do the same thing for B, and we get an average for how good that is. And then we choose the bigger one in real life, and then we get to another state, and then we do the same thing again. So this is a pretty dumb thing to do, right? Like if you're at home thinking, that's not a planning algorithm that I would choose, that's fine. It is pretty silly. It's, as I said, it's a very simplistic form of Monte Carlo planning. One way you can think about it is it's like an approximate, it's a Monte Carlo approximation to a policy improvement step on the rollout policy. So if you remember policy improvement from policy iteration, it's like we're getting a Monte Carlo estimate of the value of the rollout policy, and then we do one greedy policy improvement step off of that. And that's the decision we make. But anyway, that's what we're going to use. It's not a great planner, which actually plays into the story a little bit. So here's what goes wrong with this story. So we learned our model the way we talked about. We've got this game. The problem is, if you look at it carefully, the frames are not actually suitable for state, right? If you so say you're looking at the frame where the white dot is in the middle of the target. And then your job is to predict what's going to move, right? Which tells you where it just was. So if we do the model that we were talking about, which is like a Markov model, right? That assumes that each step is state, then it's going to get it wrong. So, and then the other thing that I'm doing here is I'm using a factored model. So each pixel is predicted independently of every other pixel based on some neighborhood of pixels around it. And that's actually sufficient in every way for this problem, except that it can't tell which direction that white dot is going to move. So in the frames where the white dot is in the middle, it can't tell whether in the next frame it's going to be on the left or the right. Right? That's the only flaw in this model. And it seems like that shouldn't be a big deal, right? It seems like, well, we can't predict where the white dot's going to be. Who cares? We can still play the game. We can still hit the targets. This is not a disaster. It is a disaster. This is terrible. So let me show you why. So if you're imagining a rollout from the model now, it starts in the same frame, but now it's going to start imagining a future. And so it imagines a next frame, which is wrong, right? It's got an error. It doesn't know which side the white dot is going to be on. And so it makes these weird predictions because it's also predicting the dots independently. So it has to do kind of a 50-50 thing on both sides. And so it's going to get it wrong in some ways. But here's the real problem. The model's never been trained on an image that looks like this. this is an entirely new image. And so if you feed that back into the model and ask it what's going to happen next, it has no idea. It's going to give you garbage. And that frame looks even weirder than the last frame. And so the next one is going to be even worse. And that one's even worse. And the next one's going to be worse, and so on and so on. So you get this progressive dissolving into chaos, right? Where you just stop being able to make any meaningful predictions. And in particular, for this game, the weird thing about this model is even though it has only this seemingly innocuous tiny error, the result of it is that it cannot imagine a future where a target sticks around long enough to be hit by a bullet. So it makes it very hard to plan with this model, right? It can't possibly advise you to shoot a bullet because it thinks all of the targets are going to bubble away before the bullet ever gets there. So this is a weird thing. It's a frustrating thing. It's sometimes called the compounding error problem, where if your model has even tiny errors, when you compound those errors and compound those errors and compound those errors by continually iterating, they blow up exponentially into giant errors very quickly. So, but there is hope. I don't want you to be completely in despair, because in the very same class of models, of factored Markov models, there is a different model that would be more desirable, right? So this is a better factored Markov model. It would do something like this. It would make the error, right? Of course, it's got to make that error. Can't fix that. But this is, again, in the same class of models. It could, in the next frame, predict that, right? It could take this unreasonable frame and predict a good next frame. So I have a question. When we studied off-policy learning, we saw that we could prevent learning from futures we think are impossible by way of importance sampling. Is there a way to stop a rollout that we deem infeasible without hindering the exploration we hoped to keep? So there's the rub, right? It's conceivable that you could detect, like, oh, this rollout is going off into Nowheresville. Maybe I better cut it off. But if your model is this lousy, oops, wrong direction. If your model is this lousy, you're not going to get anywhere, right? You have to cut it off immediately. And so, so that's an issue too, right? So you could do something like importance sampling where these, like, you know, have decreasing weight, but then you can barely use it for planning. So we'd much rather do this, right? Like make a reasonable, another error probably, but then still make a reasonable prediction. Models have the ask, oh, give me a state from the world, and then what is the error in the prediction about the next state from the world? They're both going to give you the same error. They're both minimum error, but one of them is way better than the other, and it's because the second one has way better multi-step error. It's not just good at predicting the next state, it's good at predicting 2 states from now, and 3 states from now, and 4 states from now, right? Which is really what we need. Like, we can't have this compounding error problem that just explodes. We need it to stay kind of level if we can. So the question is, can we learn this model instead of that model? And the answer is yes, but we have to do something different than we usually do. So I called this idea hallucinated training for a variety of reasons, but I'm not the only person to have thought of it. You know, there was a few years there where a bunch of different people were simultaneously kind of coming up with this idea in different contexts. But here's the basic idea. So here's a sequence in the world, right? Here's what really happened. In parallel, we'll roll out our model, right? So here's the garbage rollout that we get from our model. And so we want to train our model to do reasonable things with the unreasonable frames it generates. And the only way to do that is to feed those unreasonable frames into its learning process. So I'm going to take these two sequences of states. One of them is real and one of them is imagined. And I'm going to create data that goes from imagined states to real states. So for each imagined state, we'll train the model to predict the next real state. And so this is a different measure of error. It's called hallucinated error. It's the error in the prediction of the next real state given a potentially incorrect model state, one sampled from the model. So we're associating them like this, right? Where we think, S1 should go to S2, and Z2 should go to S3, and Z3 should go to S4, and Z4 should go to S5. We want to train them. In our training set, we'll have data points that look like this, where the input is, the input state is, here's a state that the model generated, and then the target and an action, and then the target is the state that actually really happened in the real world sequence. I'm hoping that makes at least some intuitive sense, like this idea of training the model to take these errors and kind of drive back to a reasonable state. It's not obvious that this is going to work, right? If you look at this, it's kind of bonkers. Like we're throwing a bunch of garbage inputs into our data. Is this generally a good idea? And the answer, as it turns out, is yes, you can in fact prove that this is a good idea. So I'm not going to show you the math. I'll just tell you what it does. So say we want a high quality one-ply Monte Carlo policy. It's possible to prove that in order to have that, what you need is an accurate estimated value of the rollout policy, a good rollout policy, deep enough rollouts, and enough rollouts, right? So like you need a lot of samples, you need them to be deep enough so that the discount factor washes out any remaining error. You need a good rollout policy because if you have a lousy one, then doing one step of policy improvement is not going to help you much. And most importantly, you need from your model good estimates of the value. So 3 of these don't have anything to do with the model, so I'm just going to leave those out. What does it take to get an accurate estimated model value for the rollout policy? And the answer is, well, what we really need for that is low multi-step error. So we need, in other words, for the distribution of states k steps from now in the model to be a lot like the distribution of states k steps from now in the real world. That's really hard to train on. Let's see, let me repeat that. So in the hallucinated training, is our training set constantly changing? The answer is yes. It is really strange to train on this error. You have to do a little bit of a staged training. Like you have to kind of collect some data and then train on that data and then collect some data and then train on that data. It's not so easy to do it just kind of in a tight loop. So the model gives us Zi to Zi plus 1 transitions, and our loss from the model is based on Zi to Si plus 1 pairs. That's exactly right. So we need multi-step error, but it's hard to train our model to have low multi-step error. Like the model parameters are not easily, it's not easy to tell the relationship between the model parameters and multi-step error to reduce it directly. So what people have done forever is instead reduce the proxy, which is the low with one-step error. So people have forever trained their models to have low one-step error. And it turns out if you have genuinely low one-step error, then you also, by definition, have low multi-step error. But you have to have very, very low one-step error. in order for that to matter. And so it turns out that it's possible to prove that hallucinated error fits right in between these. That low one-step error implies low hallucinated error. Like whenever you have low one-step error, you have low hallucinated error. But also sometimes you have high one-step error and still have low hallucinated error, which means that you have low multi-step error and therefore an accurate value estimate. So it turns out that hallucinated error is more tightly related to control performance than one-step error under some conditions. There's my asterisk. So there are some limiting assumptions in there, but it's at least a good indicator that that there's something here, right? That our old way of measuring model error was inadequate, right? It wasn't allowing us to tell the difference between models that are useful for planning and models that are worthless for planning. Whereas hallucinated error does a better job of distinguishing useful models from useless models. Let's see, Dave asks, well, does this work for complicated environments as well? For example, with a much larger state space? I will answer that in a second. And Maz says, very cool, thanks. I think so too. So what to do with that? Well, I took that theorem and I combined it with an existing algorithm. So it's based on an algorithm called Dagger, which is from 2012, which is significant because it was the first algorithm to promise theoretical performance guarantees, regardless of the model class. So it has a theoretical result that doesn't assume that the model will eventually be perfect. It bases its theoretical result on the best model in the class rather than assuming a perfect model in the limit. So that's a big deal because that's the setting where I live. And so, but the problem is it assumes near optimal plans. It requires that it have a planner that just always does the right thing, which is not reasonable. And of course, like most people have done, it minimizes standard one-step error. So in 2015, I extended that algorithm just a little bit. I wanted to see what would happen if we took away that assumption of near optimal plans. So I specialized Dagger to this really silly planning algorithm called one-ply Monte Carlo to see if I could make it still get a guarantee based on this suboptimal planner. But it still minimized standard one-step error. I still hadn't fully worked this hallucinated thing out. And so that brings us to hallucinated Dagger MC, which I published about in 2017, which is Dagger MC, but it minimizes hallucinated error instead of one-step error. So let me show you what happens when you do this thing. So this is the shooter example that we've been looking at. On one side, there's moving bullseyes, and on the other side, there's fixed bullseyes. So when, let's look at the right side first. So when the bullseyes don't move, you actually can learn a perfect model, right? Like in the limit, you'll learn a pretty much perfect model. So Dagger MC does great. Dagger failed miserably, and that's because broken and Dagger is a disaster. Moving bullseyes condition, now Dagger MC is also a disaster for the reasons that we were just talking about, right? The model can't imagine hitting a target, and so it very rarely decides to ever shoot a bullet. Whereas if you optimize for hallucinated error instead, you get something like this. And so you can see that hallucinated Dagger has avoided this catastrophic failure, right? It's still learning an incorrect model. You can see it's not doing as well as the perfect model in either condition, but it is learning something, like it's learning a useful incorrect model, and it's able to do some reasonable planning even though the model has errors. It's not doing quite as well. Like in the limit, the math says that hallucinated Dagger should do just as well as Dagger MC in the fixed bullseyes condition in the limit. But I think it's taking a long time because of all the noise in hallucinated Dagger's data set. So it's just taking a long time. Why is it learning an incorrect model in the fixed bullseyes problem? Oh, no, so in the fixed bullseyes problem, they're both in the limit, they will learn fully correct models. It's just taking a long time to do it. And then also Dagger is quite honestly not a super practical algorithm. It takes a long time to get to where it wants to go. So the main thing that's interesting about Dagger is its theoretical properties, not that someone would probably want to use it. So hopefully this is getting you excited about hallucinated error. But Dave wanted to know, does it work in big problems? I wanted to know that too. So going back to Atari, we did all those experiments with perfect models. Then we turned around and tried to do it with learned models. So we learned some dynamics models of these Atari games using convolutional neural nets. And then we were sure to train them with something along the lines of hallucinated training. Now, it's not the theoretically, it doesn't like satisfy all the theoretical conditions of hallucinated Dagger because that was totally impractical at this scale. But we did do something very similar, and I can sort of, you know, I don't have the plots to back this up, but it is the case that when we didn't do it, it was a miserable failure. So it did help qualitatively. So let me show you what happened in a few of these games. So these results are now with learned models. So let me just orient you to this plot. So the benchmarks are still the same. So there's the DQN with 100,000 frames, there's experience replay, and then at the top there's DQN with 10 million frames. The blue and purple bars are still the perfect model results. So they just climb up just like we saw before. And then the other ones, the dark colored bars, those are two different ways of learning a model. One of them is pre-trained on a bunch of expert data from a trained DQN agent, and one of them is learned online as the agent is learning its policy. It's also learning its model. And so you can see, first of all, that it's a little disappointing, right? It doesn't get anywhere close to the perfect model results. And there's also this interesting hump shape. So for a while there, you can see it going up as we kind of would expect it to do, because the deeper the rollouts we get, the more diversity we get in our data set, and that means, you know, we do a better job of learning our value function. But then after a while, it kind of turns around, because eventually, even with something like hallucinated training, eventually there are errors that our model just can't overcome. And so we go deeper, we get more garbage in our rollouts, and they start to become harmful rather than helpful. So we tended in a lot of different games, we saw some sign of this kind of hump shape, where there was kind of a middle ground that was like getting some of the benefit from the long rollouts, but not pushing things so far that the rollouts became misleading. So here's another game. This is Qbert. And so once again, you can see there's a moment there where it is better than experience replay, and it is for a fairly large number, deep rollouts. But then if you go deeper, it gets worse. And then Space Invaders is a game where it basically was worthless no matter what. So you see they just go down as the rollouts get deeper, and none of them are better than experience replay, and some of them are worse than just doing DQN with no model at all. So what's happening there? Well, it turns out that in Space Invaders, it's really hard to learn about the bullets because the bullets are really tiny. So it tends to lose track of the bullets, which, as you can imagine, makes it not a very useful thing for planning, because bullets are critical to the whole thing. Like, you got to avoid bullets and you got to shoot bullets at aliens. Everything else is just details. So Space Invaders, failed pretty miserably. But I want you to, like, if this is disappointing results, but I want you to just understand how amazingly baffling this is, because I'm going to now show you a video of what these models look like when you roll them out. Here's the Qbert model, I think. Yeah. So let's see. This is just a short snippet of the Qbert model rolling out. The one on the left is the model, and the one on the right is the world. Let's see, could you discuss briefly how models are learned? You mentioned convolutional neural nets, though it also seems like states have a sequential nature to them. Do you train on pairs of images of consecutive states? So, good question. So there's a whole bunch of details in the model architecture, which actually we didn't even come up with. It was from this paper in 2015 from Junhyuk Oh. But the main thing is it takes the last 4 frames and it predicts the next frame. So it's true that there's some sequential stuff in there, but it mostly doesn't care. It just, it's really just treating it as a one-shot, like a supervised learning problem, inputs and outputs, but the input does include a little bit of the past. So, I mean, if you look at this, you can see the model knows a lot. Like, this is incredible, actually, how good it is at rolling out. Like, this is a length 50 rollout, length 70 rollout. I mean, it's holding together. You can also see that it's missing some stuff. Like, it doesn't have the flashing of those little discs, the little lines on the sides, and it doesn't have this purple blob that shows up. And the scores are all wrong, but a lot is right. And so to me, it's incredible and weird that it's so bad. Like, this is terrible for how good that model ought to be. And it's very expensive too. I mean, neural nets take a lot of compute time and a lot of training, and for it to look that good and be this bad is very frustrating. Let's see, this goes to what, 230? All right, so we're definitely not gonna get through everything, and that's fine. Let me just make a couple more points and then I'll open it up to more questions. So what to do next, right? So we've hallucinated training, I think I learned something important about what you want from a model, but also I fell into a trap that people have been falling into for years. So let me tell you about the trap. So here's the universe. Here's all the problems. And the frustrating thing about model-based reinforcement learning is that the universe is basically divided into 2. There's the problems that model-based reinforcement learning can handle, and then there are, wrong thing. Then there are the problems that cause catastrophic failure. And only those 2 possibilities. And so that's largely why people don't use model-based reinforcement learning in practice in big problems, because usually it just doesn't work and it doesn't fail gracefully like model-free techniques tend to. And so I was doing a thing that people have been doing forever, which is thinking about the question, well, how can I make the model better? Right? So sometimes people do it by learning a bigger model, right? So there's this, in Atari, for instance, there's this long history of people like, oh, well, let me try this for a model. Oh, that didn't work. Let me try an even more complicated thing and an even more complicated thing. And so now we're at these giant convolutional neural nets. I think some people are using recurrent convolutional neural networks, and they're just huge and so many parameters, just making our models more and more complicated. I was falling into the same trap by trying to find a better, I don't know, loss function for my models. But either way, the result is the same. You succeed in making your model better, and then that's what happens, right? Like, you can maybe catch a few problems that you couldn't catch before, and still everything else is a disaster. And so that's not a good situation to be in. What I would much rather be doing is thinking about this question. How do we plan with wrong models? Like, let's just take it as a given that our model is wrong, that it's going to be catastrophically wrong in some cases. How do we plan anyway? How do we get the good stuff out of the model and leave the bad stuff behind? And so if we could succeed, and I'm not saying I know how to succeed, but if we could, then we could get something like this, right? We'd have a universe where in some problems, model-based reinforcement learning helps a lot, and in some problems where it doesn't really help very much, and then just a continuum between the two. That's the goal for me, right? Is to make a graceful failure for model-based reinforcement learning so it can be useful some of the time, and at least not harmful the rest of the time. So last slide I'll do, and then I'll open it up for questions for a few minutes. So to get there, I've been thinking lately about error awareness. So ideally, in order to make this possible, I need a model that knows what it doesn't know, right? That it's wrong about things, but it can also say, you know what, in these situations, I always get it wrong, right? I don't know what I don't know. And if it knows what it doesn't know, then maybe it could even refuse to make predictions, right? Or maybe our planning algorithm could take that information and refuse to use the model's predictions so as to avoid being catastrophically misled. And the hope there is that maybe we can use the model for what it knows and not be harmed for what it doesn't know. And so I was going to talk about model uncertainty and how to maybe get there, but I think that's a good place to stop and ask if anyone has any questions about what we went through. Or, you know, about reinforcement learning in general, model-based reinforcement learning in general. Okay, Mazda has a question about losses. Go for it. Is there a disadvantage to just piling on more and more loss terms? Right, that is the style these days, right? That's very in vogue. It's just like, oh, I don't know, I need another loss term. I'll be honest, I don't know. Probably. So certainly it's the case that the more complicated your loss surface is, the more susceptible you are to like local extrema, right? So you could get stuck in local minima if your loss surface is really, really wiggly. And so I could imagine that, you know, composing a whole bunch of loss functions together could cause that scenario. But I mean, I think the truth is that deep nets have really defied a number of intuitions, and we don't fully understand why yet. So just looking at it on paper, you would say, oh, these things have cajillions of parameters, and they're, you know, optimizing a really non-convex loss surface. There's no way this is going to find a good solution, and it does anyway. And one part of that story is that deep nets, so there's this interesting property of deep nets where if you make them bigger, then you get the normal thing where it's like, oh, I have more parameters, so I tend to overfit more. But then after you make it even bigger, like you make it huge, then you stop overfitting and you quickly find the correct solution. And so one explanation for that is if you make it really, really big, then probably somewhere in that really, really big network is a much smaller network that is pretty close to what you already need. Like you just randomly generated a whole bunch of parameters. If you randomly generate enough of them, some of them are going to be close to what you're looking for. And then just a little bit of gradient descent will just pop that right up to where it needs to be, and then you can just be done. So there's a little bit of like just raw compute power happening in deep nets, where if you make it big enough, you're essentially getting ultra random restarts and you're avoiding local minima that way. And maybe you can afford really complicated loss surfaces if that's your situation. Let's see, as someone who has delved into theoretical reinforcement learning, could you comment on how you feel about the state of theoretical deep learning? I was once told that the progress is led more by practitioners, but I can't help but feel like we're walking in the dark a little bit. Yeah, right. So I'll be honest with you, a lot of the results that I showed you in this talk used deep nets, but I tend not to use them a lot in my research, not that you could tell from these results, because of this exact problem. It's very hard to tell what's happening. When something works, it's not always clear why it's working. If something doesn't work, it's not always clear why it isn't working, and that's especially risky because, you know, if you're trying to do some science and you're like, oh, let me try a thing, and then it doesn't happen. And if you can't tell whether it's not happening because it just fundamentally you were wrong, or if it's because, oh, you need another max pooling layer or something, that's a problem. That makes it really hard to get any science done. So I tend to use DNets for research only when they're really necessary, because they tend to slow things down a lot, and they can cause just total breakdown of a research project. As for the field in general, I mean, obviously people are excited about this tool, and I think that's okay. I mean, I think that it's very, very powerful. It's demonstratively allowing us to do things that we couldn't do before. And so there's an awful lot of stuff out there that is just showing those things. Like, what can we do that we couldn't do before? And that's all discovery, right? Like, nobody knows what the limits of these things are. And so every time someone is like, oh, you know what? If I just do this and I re-encode it this way and I throw this extra loss function on, then I can do this that we couldn't do before, right? Like, that's interesting and important to know. I do personally think that eventually we'll hit some limits there. And some of those things will turn out to be real things, and some of them will not turn out to be real things. And hopefully, you know, there are definitely theoreticians kind of walking along behind, trying to explain some of these phenomena, trying to pick up the pieces, trying to systematize some of it. And I think that there will come a time eventually when we have, first of all, a more systematic understanding of what deep nets are doing and why they behave the way they do. But then also, I think we'll probably eventually hit some limits, find some problems that we can't really tackle with deep nets. I suspect that sample efficiency is going to be the big problem. And then people will have to go back to the drawing board a little bit, and we'll probably see a new cycle of more fundamental work of people trying to come up with principled directions to explore.
All right, that's probably a good place to cut it off after this last question of Arun's.
Okay. Let's see. Can I just? I'll just quickly answer this one.
Yes,
so
please.
Varun says error awareness sounds really interesting. Is there a recorded talk by you or someone else that goes into this, since we didn't have time today? So I was going to show you some results from a paper that's currently under review. So I can't quite send you the paper, but with any luck, there will be a new paper on this, you know, on archive within a couple of weeks. We'll see.
All right. Well, thank you very much, Prof. Talvitie. I appreciate that. I certainly found it very interesting too.
All right. Well, thank you all very much for your attention. You know, I wish we could have had more interaction, but I hope it was enjoyable, and have fun learning about more reinforcement learning.
Thanks. Just one thing to do. One thing is that the homework and the last programming assignment are both out on the schedule. So you can go take a look at that. All right, see you all on Monday. If any of you need to schedule office hours with me, feel free to just contact me and we can set something up over Zoom. All right, bye-bye.